All right, so we're going to describe the reasoning used in a hypothesis test. So what we do is we look at a test statistic. So we're talking about like a z-score or a t-score when we talk about test statistic. And what we're looking at is that when we looked at z-scores and t-scores, we can assess a probability to those scores. So we can use that probability to look at how likely it is that an event is what it is. Is really the kind of idea here. So we reject the null hypothesis when the data provides strong evidence against it. The evidence comes in the form of a test statistic. So like I said, a test statistic, there's various test statistics. For us, for the most part, it's either going to be a z-score, a student t-score, and something called a chi-square. So these are usually the common test statistics that we talk about. And these are the ones with the big focus that we've already seen. So when the difference between the test statistic and the value on the null hypothesis are sufficiently large, we reject the null hypothesis. So really kind of what we mean by that. Let me make a little picture here. Let me use a dew color because that red is not going to be great. So what we're talking about is if we have something, so we'll use this example down here. For example, we know the population mean of IQ scores is 100. So we know that this is what the population of all IQ scores are. We look at everybody, this is what we see. If we want to prove that lead exposure lowers IQ, we would need the mean from the sample, the test statistic, to be sufficiently smaller than 100 to support the claim. So what we mean by that is, let's say we collect a sample. Let's say the sample mean is, let's say it's 98. Well, 98 is pretty close to 100. That might not be strong enough to reject the claim. So in that case, that's not very strong. So that's not strong evidence. Meaning at that point that we would fail to reject the null hypothesis. So we would assume that the null hypothesis is true. Then the null hypothesis basically being, we'll put it down here. Remember, null hypothesis is where nothing happens. So we are assuming that we are going to go with that null hypothesis, which would say, well, maybe IQ does not change. It's still pretty much 100. Basically, that 98 is likely to occur. It's not very far from 100, meaning that I could collect a sample and very feasibly get a mean of 98 from the population of everybody. It's very easy to do that. So it's not abnormal. So remember that abnormal being 5%. My alternative hypothesis basically would say that we think that lead exposure is lowering IQ, so the mean should be less than 100. So let's go back here and say, well, now I have a sample mean now, but this sample mean is, let's say, 75. So 75 is roughly about here. And we know that 75 is actually 2 standard deviations below the mean. So what we'd have here is that 75 is a lot farther away. This is probably stronger evidence. So this is strong evidence that null hat is wrong. And if null hat is wrong, then we have to go to the alternative, which is that IQ scores have actually gotten lower. So we collect samples, and where these samples would come from is these would be samples of people exposed to lead. This sample is close to what the population mean is, population mean for everybody is, meaning that the sample of people exposed to lead and a sample of people who are just general people look close enough to say there's not really evidence to say the lead exposure is doing anything. Yeah, their mean's a little lower, but it's not so low that it couldn't just be simply random chance that I got it. However, if I collected a sample of people with lead exposure and their mean was 75 for their IQ, that's pretty far from 100 that we expect to collect out of most of the population. So remember that most of our means are going to be very close to 100. So getting one that's 75 seems very unlikely. So we're looking for these events that seem unlikely. It's not likely that I would randomly collect people from a population and their mean IQ would be 75, unless there is evidence that they have, unless something special about that group has lowered that IQ. In this case, it'd be lead exposure. So just an example again. So suppose an exam has been given to a large class and the instructor claimed that the mean IQ on the, or mean IQ, sorry, the mean score on the test was 80. So null hypothesis is that my mean is going to be 80. So now suppose that a sample of test scores is taken. Sorry, claims the mean score. There we go, I lost my place. Now suppose that the sample of mean scores is selected and then the sample mean is going to be 78. So 78 is fairly close to 80. So it is plausible that the null hypothesis is true. So I'd say our alternative hypothesis, since they didn't state it, is just simply that it's not 80, but we'll see what it is. So imagine, however, that the sample mean we found it to actually be 50 instead. So once again, 50 is very, very far from 80. Because 50 is so far from 80, it does not seem plausible the population mean is actually 80. So in this case, we're not trying to show that lead is causing, or lead is attributed to lower IQs. We're just saying that what this professor stated, or this instructor stated, was in fact false. They said that the mean score on their test was 80. One sample, what we have here, we forget that 78 is really close to 80, meaning we would retain that null hypothesis that, yeah, what they stated was correct. The instructor said that the mean exam score was 80, and our sample says, yeah, it looks like it's 80. On the other hand, if we collected a sample and we got a mean of 50, that's not very close to 80. In this case, we wouldn't really retain that null hypothesis. We would refute it and say, no, it's not true at all. And in that case, we'd probably go with the claim that whatever the score is, it's definitely not 80. And in fact, it's probably more likely the null hypothesis to say that score is less than 80. What we're saying is that in this case, we would end up going with the alternative hypothesis. The mean score is not 80. Our instructor lied, or maybe they calculated things wrong, but essentially what they stated was false. If our mean was 78, that is not so far from 80 that we could reject the null hypothesis. So we basically retain it and we say, oh no, the mean is actually 80. So we see that the farther the test statistic is from the value specified in the null hypothesis, the less likely the difference is due to just random chance. Like I said, it's quite easy through random chance to collect what we see all the time. That every time we collect a sample, they don't look the same. All my sample means are always going to be different, but generally they're very close to each other. So when something is not close, that means there's something a little weird for that sample. And that's what we're looking at. It's like, why is that sample weird? And that's what we're testing. So why is it weird? So really what our question is this: how big should the difference be before we reject null hypothesis? So there are different schools of thought on this. Usually, 2 standard deviations from the center is enough to say that we reject the null hypothesis. But like I said, that's not usually a standard. So what we mean by that is that if I'm looking for a mean, so the mean that is from our population, the one stated in the null hypothesis, if our population mean is over 2 standard deviations from the other one, that's usually enough to reject. That's going to change a little bit as we go through this. It's not set in stone. So to answer this question, we need methods that enable us to calculate how plausible it is to, or how plausible is our null hypothesis. The null hypothesis tests provide these methods taking into account such things as the size of the sample and the amount of spread in the distribution. And this is stuff that we kind of looked at before because we talked about sampling distributions, but looked at means and saw how likely it was to get particular means.